Welcome to the deep dive. Today, we are really getting into something fascinating, how the newest AI models, these large reasoning models or LRMs, actually think or, well, attempt to solve complex problems. You sent us some great sources, especially this one research paper, using a pretty novel method, and we're going to unpack what it tells us.
Yeah, the goal is to look beyond just the surface level performance. What's happening internally when these models generate those, step-by-step thoughts? Where do they succeed? And maybe more importantly, where do they break down?
Think of this as your guide to the, let's say, surprising strengths, but also the fundamental weaknesses that pop up when you really challenge these models.
Exactly. Forget the standard benchmarks for a moment. This is about controlled experiments. Get ready for maybe a few aha moments and probably some head scratchers too.
Okay, let's jump in. We've all heard about models like Claude 3.7 Sonnet Thinking, DeepSeek R1. They generate these detailed thinking processes, chain of thought, and the like.
Right, the promise is a big leap in handling really complex tasks, stuff beyond simple pattern matching.
But how much do we really know about what's going on under the hood? Is it genuine reasoning? Or is it just, incredibly sophisticated mimicry?
That's the core question. And the sources, especially the main paper we're looking at, highlight a major challenge with how we usually test these things.
You mean the standard benchmarks, like math problems, coding tests?
Precisely. The paper points out two big issues there. First, data contamination is a real worry.
Meaning the models might have already seen very similar problems during their massive training phase.
Exactly. So are they solving it fresh or just recalling a known pattern? And second, perhaps the bigger issue, those tests usually only score the final answer.
Right. So you get a correct or incorrect, but no visibility into how the model got there, the quality of the steps.
None at all. You don't know if the reasoning was sound, if it made logical leaps, or if it just stumbled onto the right answer through a flawed process. That lack of process insight is a huge gap.
So, okay, if standard benchmarks are flawed for understanding reasoning process, how did this research get around that? This is the puzzle lab idea, right?
Yes, and this is where it gets really clever. They turn to controllable puzzle environments.
Why puzzles specifically? What makes them better for this?
Well, a few key things. Puzzles let you precisely control the complexity. You can make a Tower of Hanoi problem slightly harder just by adding one disk, but the core logic stays the same.
Okay, so very fine-grained difficulty scaling.
Right. And crucially, this avoids that data contamination problem. You're generating novel problem instances based on fixed rules.
Makes sense. What else?
They demand algorithmic reasoning based only on the rules given in the prompt. The model can't just pull in outside knowledge. It has to work strictly within the defined system.
And the most critical part, based on what you said earlier.
The ability to check every single step. Because these are simulated environments, the researchers could verify the validity of each move the model proposed in its thinking trace, not just the final configuration.
So you see exactly where it goes off the rails, if it does.
Exactly, move-by-move verification. That's a game changer for understanding the reasoning process itself.
What kinds of puzzles did they actually use? You mentioned Tower of Hanoi.
Yeah, they used a good mix to test different reasoning structures and how complexity scales. There was Tower of Hanoi, the classic disk puzzle. Its difficulty blows up exponentially, testing recursive thinking,
Okay.
then checker jumping, swapping pieces on a line. That scales quadratically, a different pattern.
Got it.
Also river crossing puzzles, like missionaries and cannibals, with constraints on who can be with whom in the boat, scales more moderately. And blocks world stacking and unstacking blocks to reach a target state, also more moderate scaling.
So a nice range of complexity profiles and logical constraints.
Mhm.
And they compared the LRMs, the thinking models, to their standard LLM versions.
Yes, and this was key. They gave both the LRM and its corresponding standard LLM the same amount of computational resource, the same inference budget to solve the same puzzle.
And what did that comparison show? Did the thinking always help?
Well, that's where it got really interesting. They found these three distinct performance regimes, depending on how complex the puzzle instance was.
3 regimes. Okay, lay them out for us.
So first, low complexity problems. And here's the surprise. The standard LLMs, the ones without the explicit thinking steps, often did better.
Better. How so?
They were often more accurate and used fewer resources, fewer tokens. It suggests that for really simple stuff, that whole structured thinking process might be unnecessary overhead, maybe even counterproductive.
Huh. Okay, so thinking isn't always good. What about the middle ground?
That's the medium complexity regime, and this is where the LRMs really shone. Their extra thinking steps gave them a clear performance advantage over the standard models. This is where the reasoning seems to pay off.
Right, that fits the narrative better. But you said three regimes. What happens at the high end?
High complexity. And here, well, they both just collapsed.
Both.
Yeah.
Even the LRMs with their thinking.
Yep. Complete performance collapse for both standard LLMs and LRMs. Once the problems got too difficult, even generating those reasoning steps didn't save the LRMs. They hit a hard wall.
Wow, okay. So the thinking helps up to a point, but it doesn't conquer exponential complexity, whatever the scaling limit is.
Seems not. And that collapse, particularly for the LRMs, is worth digging into more.
Yeah, let's focus on the LRMs themselves now. The paper shows their accuracy just tanks, falls off a cliff beyond a certain complexity threshold for each puzzle.
Correct. It drops pretty steadily and then hits zero. But the really weird part, the truly puzzling finding, is about their effort as they approach that cliff.
Effort. You mean how much thinking they do, like how many tokens they spend on the reasoning steps?
Exactly. You'd expect that as the problem gets harder, they'd think more, right? Use more steps, more tokens, try harder.
Yeah, that makes intuitive sense. More effort for harder problems.
But that's not what happens. Initially, yes, as complexity increases moderately, they do increase their thinking tokens. But as they get really close to that point of total accuracy collapse, they start to reduce their reasoning effort.
Wait, hang on. They use fewer thinking tokens when the problem is at its absolute hardest and they're about to fail completely.
Bizarre, isn't it? They have the token budget available, they're allowed to think more, but they actually seem to give up or shorten their reasoning process right when you'd expect them to double down.
That feels significant. It implies the failure isn't just about running out of steps or computation budget.
It really does. It suggests some kind of internal breakdown in the reasoning generation process itself, a fundamental scaling limitation, not just a resource limit.
Okay, that's a major head scratcher. And since they could check every step with the simulator, what did the inside of those thoughts look like during these different phases?
Right? Looking at the intermediate steps gave more clues. For the simpler problems, where standard LLMs sometimes did better, the LRMs often found the correct solution path quite early in their thought trace.
But then...
But then they kept going, exploring other, often incorrect paths, basically overthinking it and wasting computation.
So inefficient overthinking on easy stuff. What about moderate complexity, where they did best?
There, the pattern often reversed. They might explore incorrect ideas first, and the correct solution path, if found, would only emerge later in the thinking trace, more like a search process finally homing in.
Makes sense. And high complexity.
At high complexity, the traces just showed failure. They couldn't find the correct steps or sequences at all. The thinking process itself just didn't yield a solution.
And they could track the accuracy within the thought process, too.
Yeah, figure 7b in the paper shows that. For simple problems, the accuracy of the steps within the thought might decrease over time as they overthink. For moderate problems, you might see accuracy increase for a while before it eventually collapses if the problem is hard enough.
Fascinating. Okay, beyond this complexity collapse and the weird effort reduction, did the research uncover any other sort of surprising behaviors?
Oh, absolutely. There were some really telling results around exact computation and consistency.
Like what?
Okay, get this. For the Tower of Hanoi, they tried giving the model the exact explicit algorithm to solve it. Step-by-step instructions right there in the prompt.
Wow. So basically telling it precisely how to win the game. You'd assume performance would shoot up, right? Just follow the recipe.
That's the logical assumption, but it didn't help.
It didn't help, even with the perfect algorithm spelled out.
Nope. Performance didn't significantly improve, and crucially, the accuracy collapse still happened at roughly the same complexity level, the same number of disks.
That is deeply counterintuitive. It suggests the problem isn't just finding the strategy.
It's also about executing it. Consistently following a sequence of even simple, predefined logical steps seems to be a bottleneck, even when the model doesn't have to figure out the steps itself.
Like it can't reliably keep track or apply the rules correctly over many steps, even when told exactly what they are.
Something like that.
Yeah.
It points to a fundamental limitation in procedural execution, not just planning.
Okay, wow. Anything else on consistency?
Yes. The other really striking thing was the inconsistency across different puzzle types.
How so?
A model might manage, say, over 100 correct sequential moves in a really complex Tower of Hanoi problem before making a mistake.
Which is impressive, close to the optimal solution for a large N.
Right, but then that same model might fail after only like 4 correct moves in a much simpler river crossing puzzle that only requires maybe 11 moves total.
Whoa! So it can handle a long, complex sequence in one context, but fails almost immediately on a shorter, simpler sequence in another.
Exactly. It shows performance isn't just about the sheer number of steps or some abstract notion of complexity.
It seems tied to the structure of the puzzle, or maybe how similar those structures are to things seen in training.
That seems very likely. The ability to apply logical rules consistently seems to vary quite dramatically depending on the specific type of logical structure involved. It's not a general, smoothly scaling capability.
Okay, let's try and pull this all together then. What's the big picture takeaway from this deep dive using these puzzles to probe LRM reasoning?
I think the main takeaway is that despite the sophistication of generating these thinking traces, current LRMs have some pretty fundamental limitations when it comes to structured algorithmic reasoning, especially as complexity ramps up.
We're seeing they collapse under complexity.
Right, they hit a hard wall. And they do that weird thing where they counterintuitively reduce their effort just when the problems get hardest.
They overthink simple tasks, making them inefficient.
Yeah, and they struggle with consistently executing logical steps, even when you give them the algorithm.
And their ability to reason seems very inconsistent across different types of logical problems.
Exactly. It really paints a picture of models that are powerful in many ways, but perhaps aren't the general purpose logic engines we might sometimes imagine. They seem to hit fundamental barriers.
It definitely challenges the narrative that just scaling up current architectures will inevitably lead to, perfect generalizable reasoning. There seem to be specific failure modes tied to complexity and task structure.
It does. And considering that providing the explicit algorithm didn't prevent the collapse in Tower of Hanoi, and performance varied so much between puzzles, it leaves us with a really important question to ponder, doesn't it?
Which is,
Are these limitations inherent? Are LRMs fundamentally pattern matchers that excel at statistically plausible sequences, but struggle with the kind of novel, structured computation needed for true algorithmic reasoning? Or are these just really tough engineering hurdles that the next generation of models, maybe with different architectures or training methods, will overcome?
pattern matching limits versus solvable engineering challenges. That's definitely something to think about. Thanks for joining us for this deep dive.